Hi, everybody. Welcome back officially to session 8 of Introduction to Physics. The past couple of days, we've been talking about motion in one dimension, now extending that to motion in two dimensions. And today, not just motion in straight lines either horizontal or vertical, but we're going to start seeing what happens when we launch things at an angle and how to involve trig into this um, discussion that we've been having about motion. So without further ado, let's go ahead and jump back into some of the example problems that we were doing yesterday about this motion in two dimensions. All right, here's example 3. You throw a ball vertically upward from the roof of a tall building. The ball leaves your hand at a point even with the roof railing with an upward speed of 15 meters per second. Then it is in free fall. On its way back down, it just misses the railing. So first you want to find the position and velocity of the ball 1 second and 4 seconds after it leaves your hand. So here's our picture. Again, it's a good idea to always start with a picture or just trying to visualize what's happening. Here you are standing on the roof of a building. You throw a ball up vertically and it falls back down, just missing the railing. And so we want to find the position and the velocity at these two different instances in time. So another key thing that we want to do to start off with is figure out those key bits of information that might be hiding in the scenario. So first of all, we threw the ball vertically, not horizontally, not at an angle. That is important. We gave it an upward speed of 15 meters per second. So this example is a little bit different than the ones we were doing yesterday. In the examples we did yesterday, the object started from rest and fell from rest. This time, the ball is moving up at a certain speed and then it falls back down. So that upward motion adds a little bit of complexity into the problem, but it's not too much different. So once we gave it that initial upward speed of 15 meters per second, then it is in free fall. So at that point, we're not considering air resistance or any other forces acting on the ball except for gravity pulling it down. Okay, so this just jumps into the equations really quickly, but again, these are the same equations that we saw yesterday, our kinematic equations. Remember, kinematic means of motion, so our equations of motion. Since we're dealing with vertical motion here and not horizontal motion, all of our variables are in terms of y. Remember, y is that vertical variable, x is the horizontal variable. So our position y at a certain instant is its initial position or initial height plus its initial y velocity times time plus 1/2 y acceleration times time squared. So again, thinking about the things that we know in this scenario, the acceleration in the y direction is due to gravity. So we replace ay with negative g, negative because it's pulling it downward. Again, as well, when we do these sorts of problems, we can set the coordinate system to be wherever is most convenient. So let's just say where we are standing on the roof is our 0 point. And so it'll go up from that 0 point and it'll fall down from that 0 point. But that's where we're going to be measuring the heights from, is the roof where we're starting this throw. So that means that our initial position, y0, is 0, right? That's where we set our coordinate system to be. This time our initial y velocity is not 0 because it's not falling from rest. It's positive 15 meters per second. Positive because we threw it up. Remember, we already established that down is negative when we plugged in negative g here for the acceleration. So our initial y velocity, 15 meters per second, times time, plus 1/2. Our y acceleration is negative 9.8 meters per second squared, times time squared. So this is our general equation that we'll use, and we can plug in our two different time values into this equation. For the velocity equation, I chose the simplest one that involves the variables that we know. So our final velocity, or a velocity at that particular instant, is what we're looking for. And that equals our initial y velocity plus the y acceleration times time. So again, y acceleration is negative g. Initial y velocity is positive 15 meters per second. And so this is our general equation that we'll use. We can plug in our different times and get our velocities at that location, or at that moment of time. So when we do that, when we plug in our time values into both our position equation and our velocity equation, for a time of 1 second, the position is 10 meters. So 15 times 1 plus negative 4.9 times 1 squared gives us approximately 10. And our velocity at that instant is positive 5.2 meters per second. Do the same thing for 4 seconds, just plug 4 in for t, and we'll get a position of negative 18.4 meters and a velocity of negative 24.2 meters per second. So that means after 1 second, it's still traveling upward because both our position and our velocity are positive. But after 4 seconds, it's already reached its peak and now it's falling back down because its position is lower than our starting height. And the velocity is negative, showing that it's traveling downward now. So let's find the velocity when the ball is 5 meters above the railing. Okay, so now we're given a definite final position to consider, and we need to find the velocity at that final position. So we can use this equation here. Final velocity squared equals initial velocity squared plus 2a. And yesterday I had it written as delta y, the change in the height. But whenever we have a change in something, it's always the final value minus the initial value. So our final height minus the initial height. Okay, so again, our initial velocity is 15, positive 15 meters per second, and we square that, plus 2 times our y acceleration, negative 9.8 meters per second squared. Our final height is 5 meters. Our initial height was 0 because that's where we set our coordinate system. So that's a change of 5 meters. When we plug all that in our calculator, we get a velocity squared of 127 meters squared per second squared. Is this our final answer? No, it's not, right? This is our velocity squared. So when we take the square root of this number, we get two potential answers, right? A positive 11.3 meters per second or negative 11.3 meters per second. Because remember, two negatives, when you multiply them, it equals a positive. So we have two possible answers here. And that makes sense when we think about it, because the ball passes that height of 5 meters twice. It passes it once on its way up and once on its way back down. And so when it's passing that point on its way up, the velocity is going to be positive 11.3 meters per second. And when it passes it again on its way back down, the velocity is going to be the negative down, negative 11.3 meters per second. Okay. Sorry. Hold on one second. Okay. So now, part C, find the maximum height reached and the time at which it is reached. Okay, so now we need to find that highest point, how high above the balcony that highest point is, and at what time it gets there. So this seems a little bit complicated to think about because we don't have a time to plug into our equations. We don't know what that height is going to be. We need some additional piece of information in order to make one of these equations helpful to us. And that additional piece of information that we need to remember is when it's reached its maximum height, that's when it's going to change direction. That's when it's going to go from going up to going down. And so when it goes from going up to going down, at that instant, right at the top of its trajectory, right at the peak, its velocity is momentarily zero, right? Because it has to change from a positive number to a negative number. When it changes direction, its velocity is instantaneously zero. And remembering that is going to give us that key bit of information that we need to plug into one of our equations. Okay, so that means that our final velocity is zero, right? If we're taking the peak of our trajectory to be its like final height, then the final velocity, when it reaches that point, final velocity is zero. Okay, so we're going to use that same equation that we had before with the velocities and the acceleration and the change in height, because those are all the things that we either know or are looking for. So we need to know this y variable. That's what we're looking for. Okay, the maximum height. So we'll take our equation here and do a little bit of algebra manipulation to rearrange this equation and find what we're looking for. Okay. And when we do that, remembering that acceleration is negative g. Our initial height was 0, so that kind of leaves our equation. So that gives us a new equation for maximum height of initial velocity squared divided by 2g. So our initial velocity, 15 meters per second squared, divided by 2, 9.8. That gives us a maximum height of 11.5 meters. So that's how high it will go when the velocity is momentarily 0 and it changes direction from up to down. So that is its maximum height. Now, trying to think about how to find the time at which it reaches that point. We can use pretty much any equation that involves time now. We should have everything else that we need. So I picked the simplest equation that had the time variable in it. So that was our final velocity equals initial velocity plus acceleration times time. So our final velocity, remember the velocity at the maximum of its trajectory, the maximum height, is 0. So By, its final velocity is 0. Our acceleration is negative g. So again, rearranging this equation to get t by itself, we get initial velocity divided by g. And so that's 15 meters per second divided by 9.8 meters per second squared. So that happens at a time of 1.53 seconds after we have thrown it up into the air. Okay, so those are our two answers to part C of this example. Whew, that was a big one. Do you guys have any questions about any part of this example problem? As always, if you have questions, feel free to type them in the chat. Interrupt me while I'm talking, totally valid. Um, or you can hang out after class and ask me then. For now, we'll keep rolling. Find the acceleration of the ball when it's at its maximum height. Now, this is kind of a trick question, a little bit, because we really need to understand what the meaning of acceleration is here. Remember, acceleration is the change in velocity over time. And everywhere that an object is in free fall, the acceleration is acceleration due to gravity, which is negative 9.8 meters per second squared. Now, that might seem kind of strange because when it's at its maximum height, the velocity is zero. So isn't the acceleration zero? No. If the acceleration were also zero at its maximum height, the velocity would not be changing, and the ball would just magically hover in midair at that point because the velocity cannot change without an acceleration. So it would get to the maximum height and then just freeze if both the velocity and the acceleration were zero. Okay, so that's a really common misconception that people have. It is totally valid to have a velocity that's instantaneously zero and an acceleration that is not equal to zero. Okay, so here's another question. I want you guys to give this a try. I've written down the equations that we talked about yesterday, the kinematic equations here in the orange box, and then some hints for you. Identify your variables, draw a sketch, be careful with your signs. So make sure you establish which direction is positive, which direction is negative, where your coordinate system is. So your 0 point can be wherever it's most convenient. But I want you to take a couple of minutes, think through this example, and try to set it up on your own before we go through the answer together. If you have questions, feel free to message me in the chat. All right, so this would be a pretty typical homework type problem that you guys might see. I think I took this one from the back of the textbook, like the chapter questions. So this is a pretty good example of like your stereotypical physics 1 question. So we have a spacecraft landing on the moon. That's important because the moon will have a different acceleration due to gravity than Earth does. And in fact, it specifies it right there for you in the problem. The acceleration due to gravity on the moon is 1.6 meters per second squared. So that means anywhere we see an acceleration in the problem, we are not going to use 9.8, we are going to use 1.6. Okay. It's landing, so it has a downward velocity of 0.8 meters per second when it's 5 meters above the surface. And we want to know at what speed it hits the ground. So looking at this problem, we don't know anything about the time, but we do know the change in height, 5 meters, the initial velocity, the acceleration, and we're looking for the final velocity. So knowing those things, the equation that would probably be the best to use for this problem is equation number 6 down here, because that combines everything we know and does not involve time, which we don't know. So drawing our quick little sketch here, we have our spacecraft landing with a velocity of negative 0.8 meters per second. So again, I've labeled that V0y, our initial y velocity. It's at a height of 5 meters above the ground. So here you could have chosen the ground as your 0 point. You could have chosen the spacecraft as your 0 point. It really doesn't matter as long as you're consistent throughout the whole problem. But our change in height here is negative 5 meters based on the coordinate system that I chose. So here we have equation 6. Our final velocity squared equals initial velocity squared plus 2 times acceleration times the change in height. So I took the square root of both sides so that we get velocity by itself. And now we just plug in the things that we know. Initial velocity is negative 0.8 meters per second, and we square that, plus 2 times our acceleration, and since down is negative in my coordinate system, I give it a negative 1.6 meters per second squared. Our change in height is negative because the 0 point is up where the spacecraft was. And so that gives us a velocity of 4.08 meters per second downward. So yeah, I have the answer as a positive value just to point out the fact that it's very easy to miss points here by not specifying your direction. So intuitively, it should be pretty obvious that this spacecraft is traveling downward. So the answer would be negative. Your calculator, on the other hand, will give you the positive root instead of the negative root, most likely. I mean, your calculator might be a little bit different, but my calculator gives me a positive root. So you're going to want to make sure that you pay attention to those sorts of things. And remember, if the object is moving down or left or west, one of those negative directions, your velocity will be a negative answer, even if your calculator gives you a positive value. Okay, next part of this problem, same setup, but now how long does it take to land? So now I want you to take a moment, try to find the time that it takes. I'll give you a minute to think about it. All right, that was probably a quick minute, but we're gonna go through this just for the sake of time. And for those of you who are watching this video not live, Tristan pointed out that the question asks, at what speed does it hit the ground? So in this case, the negative that is implied by it traveling downward doesn't really matter because we're asking for speed, which is just the magnitude anyway. Way to go, Tristan. Okay, so this problem, how long does it take to land? Now we're thinking about a time. The equations that we could potentially use are 3, 4, or 5. But there are definitely some that are much simpler to use than others. And I would always argue that it's better to use the simpler one than a more complicated one. So here's our picture again. We now know the final velocity, which is negative 4.08 meters per second. And so the simplest equation that well, in my opinion, the simplest equation that involves time is this one, which would have been your equation 3. So final velocity equals initial velocity plus acceleration times time. So if we rearrange this equation to get time by itself, we get final velocity minus initial velocity over our acceleration. So our final velocity is negative 4.08 meters per second minus initial velocity of negative 0.8 meters per second divided by our acceleration of negative 1.6 meters per second squared. And that gives us a time of 2.05 seconds to land. Now you might look at this equation, and if you're clever, you might realize that this here is the way that we calculate the change in velocity. So that delta V, this time that we're thinking about is really a change in time from the 0, like when we start the stopwatch at 0 point to when it lands on the ground 2.05 seconds later. That's our change in time. So if we look at our equations here, what we really did is took equation 2 and rearranged it to solve for delta t. We ended up at the same point with equation 2 as we did with equation 3. Remember, these equations are all related to each other. And so we ended up doing basically the same thing here. Okay. So now that we know the basics of motion in one dimension and two dimensions, we can really extend them to as many as we want. So instead of looking at just horizontal motion now, or just vertical motion, we'll see what happens when we combine those things together. All right, so here's our horizontal motion. Here's our vertical motion. Here's our combination. Now, I don't recommend that you throw cats, but they do make a good example. So a question for you guys to think about, and if you've taken physics before, you might know the answer to this, but this is one of the biggest misconceptions in this whole unit, I think. So what hits the ground first? A ball is dropped from 1 meter high. At the same time, another ball is fired horizontally at 3 meters per second from 1 meter high. Which one hits the ground first? So take a quick second, pick an answer in your head. You don't need to type it in the chat or anything. Just pick your answer. And then let's talk about it. So to illustrate this point, I have two videos. Just for the sake of time, I probably don't have time to show them in class, but I'll post these notes on Canvas so that you can go and look at these videos yourselves and kind of verify our answer. This top one is a experiment, well, more a demonstration that a professor did at a university. And then down here is a link to a Mythbusters episode. But it said like Mythbusters for the impatient or something. So it takes basically the whole episode and shortens it down to about 2.5 minutes. But take a look at those videos if you're curious to see this in action, because really they hit the ground at the same time. It's crazy. It's just astonishing. And I just like I've been teaching physics for 6 years, 7 years. I don't know. Time has no meaning anymore. Thanks, COVID. But anyway, it just amazes me like how many people just get their minds blown from this idea that these two balls hit the ground at the same time. And so the key takeaway from this is that our horizontal motion, right? One of these balls is fired fairly quickly. That horizontal motion has no impact at all on its vertical motion. And so a ball that's dropped from rest and a ball that's launched horizontally will hit the ground at the same time because gravity is pulling on them both in the same way. They both have the same acceleration due to gravity. They both have an initial y velocity of 0, right? One has an x velocity, but initial y velocity of 0. So in a sense, it's like they're both falling, like free falling, even though one is fired and one is dropped. It's very interesting. So basically, X and Y they don't care about each other at all. And it says here, notice how the balls continue to bounce at the same moment as well. You'll see that in that first video link that I posted. So even though one like continues moving to the right, you can hear it. They still bounce and hit the ground at the same time, despite one's horizontal motion. So velocity and really motion in the x direction is not related to velocity in the y direction. They are independent of each other. They both have the same y acceleration as soon as they leave your hand or the gun or whatever is firing it, but they are independent of each other. And so what that means for us when we're dealing with objects that have both horizontal and vertical motion at the same time is that we must examine them separately. We can't combine x variables and y variables together in the same equation because they're not related to each other. Like they don't interact. They don't affect each other. They're independent. So we have to treat horizontal motion and vertical motion separately before we can even think about combining them to see what the overall motion is. So now we're going to take some of our old kinematic equations and rewrite them in a new way. But you'll notice that really those equations don't change very much. It's just now we have these little subscripts, which I'd been using in previous examples anyway. But the equations stay the same format. We're just specifying x direction or y direction, right? So delta x becomes delta y, vx becomes vy. We have to specify which direction this particular information deals with. So as you look at example problems now and try to identify those key bits of information, it's going to be important for you to identify if it's horizontal x motion or vertical y motion. The only really real thing that we see linking these two sets of equations together is the time, right? There's no time in the x direction and time in the y direction because when it hits the ground traveling in the x direction, it's hitting the ground traveling in the y direction too. Those times are the same. And so time is really that linking variable from one set of equations, from one direction to the other. So that's going to help us. Yes, it's just going to help us knowing that time is the same. Time is our linking variable. Everything else we have to keep separate. Okay. So now thinking about things that we have talked about previously. So vectors last week in chapter 1, right? We learned how to take a vector and break it apart into its components. Remember, these components tell us about its horizontal and its verticalness, right? How far to the side this vector goes, how far up or down this vector goes, those are the components. So now if we're thinking about a specific vector like velocity, and let's say we're launching something at an angle now, so firing a cannon or I don't know, shooting an arrow or what have you, throwing a cat, you know. I love cats. Just please, like, don't think I hate cats. I'm allergic to them, but I love them. Anyway, when we have our vector, we can break it down now into its y velocity and its x velocity using those same rules, those same tricks that we talked about in chapter 1 vectors. So I don't have it here on this slide, but remember last week I talked to you guys about SOHCAHTOA, SOHCAHTOA. That's the way that helps me to remember these trig identities, which sides of a triangle correspond to the sine or the cosine or the tangent. So if we're given this initial velocity at some angle, theta, that initial velocity, you can kind of see it's the hypotenuse of our triangle, right? It's the longest side of our triangle. So thinking about these trig functions, right, this x component is the side of the triangle that is adjacent or next to our angle. And so SOHCAHTOA tells us that if we know the hypotenuse and if we know the angle, we can find the adjacent side of the triangle. So we can find that x component of the velocity. right? So the x component of the velocity is the hypotenuse, initial velocity, times the cosine of our angle. Similarly, right, this y component, we can, remember, we can take a vector and slide it as long as we don't change the length or direction. So if we take this arrow here and slide it all the way over, you can see how it kind of completes our triangle here. And it becomes the side of the triangle that's opposite our angle. So patoa tells us that the sine of the angle is the opposite side over the hypotenuse. So if we're trying to find information about the opposite side and we know the hypotenuse, then we're going to use the sine of our angle as our trig function. So our y component is the initial velocity times the sine of our angle. Okay, if we didn't know the initial velocity at all, but we did know the one of the components and the angle, then we could still find the other one using the tangent, right? Tangent of an angle is the opposite side over the adjacent side, TOA. Okay, so don't forget about those trig identities. They are helpful to you now in projectile motion. And so these are the equations that we just outlined here in our picture. But if we don't know the direction, we can find it using the inverse tangent of the y component over the x component, just like we had seen in chapter 1. So now, again, putting this in terms of variables that we're using currently, our velocities. X velocity is initial velocity times the cosine of the angle. Y velocity is the initial velocity times the sine of our angle. And our angle is the inverse tangent of our y velocity over our x velocity. So when we're doing example problems like this, and we're sketching out our scenarios, we're always going to measure our angle from the positive x-axis up towards the positive y-axis. So that's going to be our basic rule of thumb for this type of problem about how we measure our angles. Okay. So let's think through some things. What's the acceleration here? I throw a ball at an upward angle. So what is the acceleration of that ball in the x direction and the y direction after it leaves my hand? So we're going to assume that our positive direction is to the right and our positive y is up. So take a second, think through this to yourself. What is our acceleration of the ball just after it leaves our hands? All right, hopefully that was enough time for you to at least think through this a little bit. So here's our correct answer. Our acceleration in the x direction is 0. So we're looking at the moment of time after the ball has left your hand. So there is no, and we haven't talked about forces yet, but there is nothing actively pushing on the ball in the x direction as it's traveling through the air. Again, we're assuming the ideal case, ignoring air resistance. So that would give us an x acceleration of 0 meters per second. There's nothing changing its velocity in the x direction anymore. There is something changing its velocity in the y direction, though, and that's the acceleration due to gravity, right? Gravity is always going to be pulling it down towards the center of the Earth. We always have to consider that, even in free fall, when we're not considering other forces. So that would give us a y acceleration of negative 9.8 meters per second squared. So we can have an acceleration in one direction and not have an acceleration in the other direction. And really, this is true of almost every example that we will do together and that you will see in Physics 1. Because whenever we're launching something, almost always we're looking at the moments of time after it has already left your hand or the gun or the cannon or the catapult, what have you, right? So if there's no air resistance, if there's no other thing pushing on the ball sideways, then that sideways acceleration is 0. Vertical acceleration is negative 9.8, assuming we're on Earth. And really, this does simplify our equations quite a bit. Because if you think about those kinematic equations in the x direction, that means anytime you see ax, acceleration in the x direction, it's automatically 0, right? After it's left your hand, there is no acceleration. So that really simplifies the math quite a bit in some of the examples that we'll do together, I guess, on Tuesday, because remember, we don't have class on Monday. But do you guys have any other questions before we wrap up for your extended weekend? All right. So again, feel free to hang out after class, ask me whatever questions you might have. Um, Quick reminder for those of you who came in a little bit late today, we don't have an enrichment session tomorrow, and we don't have class on Monday in observance of uh, the 4th of July. So I will see you guys again. Well, I guess you'll see me again on Tuesday at 3:30. I hope you guys have a great extended weekend and enjoy your 4th of July. Bye.
You